Hi, it's me, Hi Long, and I'll be talking about Rust concurrency with Gary.
Hi, I'm Ping. So I will be explain some concept in Rust concurrency and also run through some code sample to demonstrate it. So first, we have a quick overview of important Rust semantics. The first thing is the the ownership mechanism in Rust, which make it impossible to make memory leak program, and also Rust has no data race. Second is pointer and reference. The pointer in Rust work pretty much the same as in C, and the reference is like a constant pointer. Once it gets created, point to an object, you can't really change it point to another object, and it can't be point to now.
Okay, so how does Rust actually do this? Well, Rust does this with a concept that is very similar to C++ called resource acquisition as initialization. This essentially means that we move data around. And this also has an important consequence. Since we move all the data around, all data has a singular owner. And this singular owner can be scopes or objects. And the important part about this principle is that when these objects destruct, or when the scope is over, all the data that they own is also automatically destroyed. As for references, we have two types, immutable and mutable. Immutable references can be aliased as many times as possible, but you can't actually edit what the reference is pointing to. So they're only good for reading. Whereas mutable, you can edit what it's pointing to, but you can only have one.
So in this section, we will introduce some high-level concurrency construct. Despite this being primitive concurrency construct, the semantic of the Rust enforced more safety and implemented with the standard library as a higher level construct. This means they have more safety and by default implement useful concurrency features.
So the first primitive we'll be talking about is the thread. The most important thing to know about the thread is the spawn function, which essentially starts and gives us a new thread. In this code sample, this will be a very basic demonstration of bus semantics and a thread. So we have two vectors here, one which I've called moved vec and another which I've called reference vec. So this thread which is spawned has this keyword move right over here. Now it's going to capture whatever it sees from the environment that I have put inside the thread's closure, which is this anonymous function here. In particular, we have captured the mood vec. This means that this mood vec is now belonging to the thread. The thread is now the owner of the mood vec. So if we were to try access it outside in the main thread, it would result in a compile error. Furthermore, with this reference thread over here, this is also another thread that we've created, but we're not going to move the reference thread. We're simply going to store a reference of it. We're not going to change the owner. Rather, this just has a reference to something owned by another thread. Rust won't let this compile either, and that's particularly because in this case, since the main thread is the owner, it's possible the main thread might actually destruct before this thread and give us a dangling memory pointer. Another important type that we need to cover is the atomic reference counter. So because we actually can't store multiple references between threads normally, and because objects get their ownership taken away, we need some way of manipulating information between threads. Essentially, it gives us clones to the same reference that points to whatever memory it wraps, but it also has an internal counter. And this internal counter ensures that the object or reference it is holding is absolutely destroyed when there is no existence of any references in any scopes or objects. And in this example, we will have a string, hello, and we will have a reference counter wrapping it. And for these five threads, we will give it a copy, a clone of the pointer that is wrapping it by the atomic reference counter. And this is allowed. The reference counter will make sure that this memory does not actually get leaked anywhere. And as a result, we can have five threads storing this memory uh, hello at this and access at the same time, but note that we can't edit it. In the second example, we have a another reference counter, but it is instead wrapping an atomic integer essentially. And the difference is, while we couldn't edit the first one, we can edit the second one because it only has atomic actions to edit this object, and as a result, we can have not only references of it across threads, but there will be no possible interleaving because all the actions are atomic, so this item is safe to be mutated across threads as well.
Why do any of this? Due to Rust semantics, it can be shown if we attempt to write some code which could potentially be erroneous. The program simply don't compile. These semantics entirely remove data races, memory leaks, and make debugging easier by turning potential runtime error into compile error. This makes Rust an ideal language for modern programming of concurrency. It's easier and safer for programmers to produce concurrency software. So for the mutex in the Rust, it's pretty much similar to regular mutex, and you can do a lock operation on it to lock the mutex. And we demonstrated with a code sample. So for this code sample, we create a mutex called a number, and first we create a thread and move the number mutex into the thread, and we do a lock the thread, and after the lock we have like a operation on the critical region. So in this case we just add some number to the sum, and then we don't have a unlock operation because due to the ownership semantic, after the thread is done all its operation, the lock will be automatically destroyed. So simple mutex. Even a simple concurrency primitive like a mutex has some added benefit due to Rust semantics and has a higher level implementation than on the surface. Now, hopefully, you are used to Rust semantics, so we are more fast through some other primitives.
Okay, so what we have here is a channel, in particular multi-producer but single consumer channel. This is essentially a channel where you can only have one receiver but many transmitters. We're used to channels because they would have been taught with the Promella component, so we'll just jump straight into the code. It's a bit hard to see from here, but essentially we have the pipeline sort from part 2 of this assignment done in Rust using the same channel-like feature. Moving on, we have the condition variable, once again something that we're used to and we've also seen throughout this course. So in this code segment, we have this thread that particularly this thread wants to become active once 3 threads have started, but we're going to start 10. So we have a condition variable that tracks the number of threads that have been started, and every single time a thread gets started, we increment and the condition gets updated, and once the condition is finally satisfied, the thread goes through as you can see. Then we have a barrier, which is also once again very similar to the barrier we have been taught to this course. Then we have a read write lock, which is pretty much a higher level implementation of mutex. It's very much the same, except you can have multiple readers, and we'll see here that we do have multiple threads reading it at the same time, but because we still want to enforce mutual exclusion, we can only have one thread writing to it, and no thread can actually write to it while it's actually being read at all. So this is just kind of useful if you want extra functionality over mutex. And then we have future, which is not actually a construct defined, but rather it's like a trait. A trait is kind of like some sort of interface that you can extend and define. And if you were to use this, you would define you would find a function poll to return one of two predefined enums, which is async ready, async not ready. The difference between this and a standard, I guess, blocking semaphore is that this state tells you whether it's ready or not, and you can not decide to block your software or program if it's not ready. You can continue to do some other part of the code, and then when you eventually loop back and you call the function and it returns ready, then you can execute whatever other piece of code you want to execute.
So basically, networking. The standard library in Rust offers support for networking with socket and addresses, and also support TCP and UDP. So we will look at it with a code sample. in this sample, we have one program called TCP client, another called TCP server. So what TCP client do is it creates a TCP stream connected to an addresses, and when it run, it read any input from the console, and after it's read an input from the console, it sends this string to the server. So in the server, it listens to the specific address, and it just prints the message it received to the console, and the output we can see it's working as we expected. Beyond the standard library, Rust Semantics has its standard library provide less error-prone, complete, feature-rich, and easy-to-use high-level construct that acts as a concurrency primitives as well as some actual high-level concurrency primitives. But this is essentially all is in the standard library. Other libraries like Rayon and Crossbeam, we will uh, demonstrate with some code sample. So first, Rayon allowed you to do parallelism computation, run multiple tasks simultaneously. Parallel iterators traverse data container and access data elements. Rayon allowed this behavior in parallel. Rayon make it simple to use. And it has a join operation attempt to execute satellite closure simultaneously. So in this code snippet we provide, we can see we have two lists with each with 10,000 elements. First, we initialize the two lists. Then we operate them we square each element in the list. So for the first operation we did in parallel. So which means like if you have multi-core in your computer, and it will assign the task automatically on each core. And second operation is just a normal iterator, do it sequentially, and we can look at the output. If we do the task in parallel, it's 3 times faster.
In addition to Rayon, there's also Crossbeam. Crossbeam offers a few high-level concurrency constructs, multi-consumer channels, because we've had single consumer. Now, Crossbeam will give us multi-consumer channels, so I mean that's just nice to have. And we'll have thread parkers, and thread parkers are essentially like a spin lock. It's like a thread can park at a specific point, and this construct will manage a token. And whenever that token becomes available, all threads which are parked will automatically check and then automatically unblock when such token is available. In closing, Rust is a language with semantics such that it can enforce safety when programming concurrently. It's also designed to be readily extensible, so there's many libraries offering many concurrency constructs, and because of these factors, this is why Rust would be favorable to use for concurrent programming.